Got a typical rates question to go through. I'm pretty certain one of these is going to come up on the A-Level Chemistry Paper 1 next week, so it'll be a good idea to look at how to tackle something like this. So it's the classic question where you've got the different concentrations of the reactants and we've got the different initial rates. And we've got to calculate the orders of reaction for the three reactants. We've then got to come up with the rate equation and we've got to calculate the rate constant. So, where do we start? So the first thing we need to do is find a couple of experiments, ideally where you can hold two of the reactant concentrations constant and just vary one of them. And we can do that for Br minus because 1 and 2 you can see it's changing its concentration, but the other two are remaining constant. So those two experiments will help us get the order with respect to Br minus. So in terms of how we present our answer, all we need to do is something like this. So we need to just say which experiments we're using. So from 1 and 2, the concentration of Br minus has gone up 3 times. The rate has gone up 3 times. So that's a first order relationship for Br minus. So that's all you would need to write for that one. A little bit trickier for the next two. So we're going to look at the order with respect to BrO3 minus now. So you can see in blue there I've used 1 and 3. I'll write all this up at the bottom like I have done there. I just want to explain this. So you can see in 1 and 3, H plus concentration hasn't changed, so it's a good pair of experiments to use. We know the order with respect to Br minus. We've just established that it's first order, so we can factor that in. And the concentration of the BrO3 minus is halved. The overall rate change is, well, it stayed the same, so it's a ×1 change. So there's that written up in the same format as that, but you can notice I haven't said what order it is yet because we want to bring the maths into play now. So that overall rate change of 1 has been brought about by the combination of the changes in the concentration raised to their respective order power multiplied together. So we've doubled the concentration of Br minus, it's first order, and we're multiplying that by the change in concentration of BrO3 minus, so it's been halved, raised to its power. Remember these powers, these orders at A level anyway, can only be 0, 1 or 2. So basically we just need to work out, well, which of these orders is going to give us an answer of 1. And the answer is 1, because if that power was 1, so 2 to the 1 is 2, multiplied by a half to the 1, which is a half, gives you 1. So it's first order with respect to the BrO3 minus. So we just need to go back to the table to get the final one, the H plus. Just quickly talk through my choice of experiment. So you can see I've gone for 3 and 4. And that's basically because the concentration of the BrO3 minus is kept constant, so we don't have to worry about that one. So what's Br minus concentration done? It's halved. What's the H plus concentration done? It's gone up 5 times, and the rate has changed by 12.5 times. So there's all that written up, but we'll just explain the order with respect to the H plus. So again, I'm just treating that as X. So the overall rate change is 12.5. We've halved the concentration of Br minus, but it's first order, and we've multiplied the concentration of H plus by 5, and this order here can only be 0, 1 or 2. So which power is going to work? And the answer is 2. Let's just check. So half to the 1 is a half. 5 squared is 25. Half times 25 is 12.5. So that's the order. So second order with respect to H plus. So now we've got all 3 orders, we can write the rate equation and then we can calculate the rate constant. So we'll do that now. So there's my rate equation. Rate equals K, concentration of Br minus. I haven't bothered with a power 1 there, you can if you want. Multiplied by the BrO3 minus concentration, again first order, multiplied by the H plus concentration, second order. So we rearrange that to get K, so rate over the concentrations. You can use any row you want because this was all done at the same temperature, so K will be constant. I'm just going to use row 1. So there's all the numbers in, and I'm getting a numerical value for k at 16.4 to 3 significant figures. So what I need to do now, and it hasn't asked us to do it, but we must do it, is work out the units. So if we look at how we calculated k, rate over concentration, and we've got 4 lots of concentration effectively multiplied together. So units wise, we've got the units of k on the top, and we've got the units of concentration to the power 4 on the bottom. So we can sort of simplify that a little bit. So we can cancel that moles per decimeter cubed out with 1 on the bottom, so that becomes moles per decimeter cubed on the bottom. So when you expand that bracket, the moles per decimeter cubed becomes mol to the 3 dm to the minus 9. And all I need to do now is basically take that up to there. So everything's on the top line, and we just change the sign in front of the powers. So there's the units there, mol to the minus 3, dm to the 9 seconds to the minus 1. Hope that was helpful. I've done absolutely loads of this style of question on my YouTube channel, so go and check those out if you want. All right, cheers, bye.